In this section, we're going to take a look at exponential functions. An exponential function is a function where the base is a positive real number and the exponent is a variable. So if we're given an exponential function, it would look something like this. F of x equals a base that is a positive real number to an exponent that is my variable. Okay, we may see an exponential function that looks something like this. F of x equals 3 to the x power. Now the 3 would be our base and the x would be our variable. Let's say we want to evaluate this exponential function. Let's start with f of 2. If I wanted to evaluate f of 2, I would take 3 and my x would be a 2. So 3 to the second power, which is 9. That means we have the point 2 comma 9, or f of 2 is equal to 9. If we want to evaluate f of 0, we would plug 0 in for the exponent. 3 to the 0 power is the same as anything to the 0 power, which is 1. Now, this will really test your knowledge of negative exponents. If you have 3 to the negative first power, make sure you know your rule of exponents. That negative power does not make the number negative, it makes the number a fraction. So 3 to the negative first power is 1/3. On this last one, our x values do not have to be integers, they can be any value. So let's go ahead and plug in f of 1.67. So that means here we would plug 1.67 in for the x value. The only way you can actually solve this problem is by a calculator. You cannot just do it in your head. So if we go to do this, 3 to the 1.67, I'm going to round that to 2 decimal places, is 6.26. After we evaluate exponential functions, the next thing that we should take a look at is what the graph of an exponential function looks at. We're going to take a look at some specific properties that exponential functions have, and in particular the base exponential functions. So, if I am given the graph f of x equals b to the x power, remember that b is any real number that is positive. This exponential function always goes through the points 0, 1, and 1, whatever the base is. So that is the first thing that you need to know about exponential functions. If nothing is being done to the x, or the b to the x, they will always go through the point 0, 1, and 1b. The other thing that you should know here is that there's a horizontal asymptote at y equals 0. And then your graph will look something like this. So you have your graph. You will go through the point 0, 1, and 1, whatever your b is. I'm just going to put it arbitrarily up there somewhere. And then you have this horizontal asymptote in red. Then your graph will go through those points and look something like this. It will get big really fast. So this is always the general shape of your graph. Your shape can end up going this way if your b is a fraction smaller than 1, but then other than that, it will always start at the left and go exponentially bigger to the right. Let's try an example here where we want to graph f of x equals 4 to the x power. Well, we know that f of x equals 4 to the x power is going to go through the point 0, 1, and 1, whatever the base is. In this case, our base is 4. So, we have this graph. 2, 3, 4. So we're going to go through the point 0, 1, 1, 4. Don't even worry that I accidentally slanted that up. My finger got stuck on the screen. Okay, and then we are going to have our horizontal asymptote on the axis here. Okay, and then the last thing is that you are going to get exponentially bigger, and then as you get closer to the asymptote, your graph will get, or as you come down, you will get closer and closer to that asymptote there. And there's our graph, f of x equals 4 to the x. Now we can do some alterations to that graph. We can move that graph left, right, up, and down by doing things to the function. I'm just going to show you one instance where that can happen. So let's say I have f of x equals 4 to the x power plus 1. And I want to graph that. So what's going to happen if we just take a look at our a couple points here. If I plug in -1, 0, 1, and 2. And these are just some basic t-chart points. I plug -1 in here. I get -1 for x. 4 to the negative first power is 1/4. So 1 plus 1/4 is 1 1/4. I put that as a mixed number so I can find the location a little bit easier. Now I'm going to plug 0 in. 4 to the 0 power is 1. 1 plus 1 is 2. If I plug 1 in, 4 to the first is 4, plus 1 is 5. If we were to plug 2 in, 4 squared is 16. 16 plus 1 is 17. I'm actually going to graph this point on the same graph I did up here. So if I have -1, -1 goes through 1 and 1/4, so that will be about right there. Then I have the point 0, 2, about right there. Then we have the point 1, 5, that's up there. And I can't really graph the point 2, 17, it's way too high, so I'm just going to stick with this. What happened to our graph is that the whole thing got shifted up 1 because I did this adding 1 on the outside. Okay, now if I were to subtract 1 from that function, I would move the function down. We can move the graph left and right. That would be by adding or subtracting a value on our x, and the best way to go about that is using a t-chart. I want to show you one real-life situation here that can help us with this graph, or help us understand exponential functions. All right, this question says, a city has 6,000 people and has been growing at a rate of 2.3% annually. Use the equation below to find out how many people will live in the city in 15 years. This is an example of a continuous growth situation. So this 2.7 represents our natural number e, which represents continuous growth. So if we want to solve this problem, and we know we have 6,000 people, we have our continuous growth number, and our percentage rate is 0.023 and times t, for t is number of years. Then we can figure out how many people will live in the city after 15 years by simply plugging 15 in for t. So we get 6,000 times 2.7.023 times 15. And assuming I did my calculations on my phone, right? That was the calculator I used. We get 8,452. Now, it actually was a decimal number, so I rounded down because you can't have a portion of a person. So there we go. 8,452 people after 15 years. That is it for the section on exponential functions.